All right, physical science kids, Mr. Tima here with your last part of your wave notes for this section, and that is the Doppler effect. You've actually heard the Doppler effect more times than you've ever known, but you didn't even know about it. Okay, so the Doppler effect leads to something else called redshift and blue shift, which is super important, which we talked about during astronomy, but it may not have made sense, but now it probably will. So here we go. All right, the Doppler effect is like anytime a fire truck or ambulance or anything, cop car, anything goes by you. You ever notice when that fire truck, ambulance, or something is coming at you, like observer A here, it is like ear piercing. It hurts your ears so much. If you're in a car, you can hear it coming a mile away. It sounds like it's getting louder and louder and more intense and everything. And then as soon as it goes by, it doesn't sound as loud. You can still hear it, but it doesn't sound as loud. Well, you got to think this is a moving object now. It's not just an object sitting there. This object is moving. So even though it's shooting out sound at the speed of sound, it kind of catches up to that sound as it's moving towards you. The opposite is true. As it passes you, it's emitting sound at the same speed, but that sound's getting farther away from you. So you feel this drop in pitch. Okay? You'll hear that here in a second. So what we say is as the cop car is coming towards this guy here, we say it has a very small wavelength. You can see that, but a very high frequency, or that pitch is really high. When it passes you, the wavelengths are getting longer, which means the frequency is going down. So the tone or the pitch may seem as if it's much lower. You can we actually, and what would happen is if the cop car actually goes faster than the waves is producing, we say it breaks the speed of sound. Well, some of you are going, well, what does that sound like? If you've ever been to an air show or anything, they do this all the time when they do some sonic booms here. So let's listen to a couple. Okay.
Watch the vapor build up on this airplane. Look at that. Oh, yeah.
So when they say the vapor, I mean, literally what's happening is the plane is actually passing through the particles of the air. It's going faster than the sound can push the particles of air. It's not so much vapor as much as it is literally oxygen particles and everything. It's going faster then. When those things are cruising at that speed, you'll see the plane go by and then you'll hear the plane go by later. All right, here's another little video to explain that idea.
Humans have been fascinated with speed for ages. The history of human progress is one of ever-increasing velocity, and one of the most important achievements in this historical race was the breaking of the sound barrier. Not long after the first successful airplane flights, pilots were eager to push their planes to go faster and faster. But as they did so, increased turbulence and large forces on the plane prevented them from accelerating further. Some tried to circumvent the problem through risky dives, often with tragic results. Finally, in 1947, design improvements such as a movable horizontal stabilizer, the all-moving tail, allowed an American military pilot named Chuck Yeager to fly the Bell X-1 aircraft at 1,127 kilometers per hour, becoming the first person to break the sound barrier and travel faster than the speed of sound. The Bell X-1 was the first of many supersonic aircraft to follow, with later designs reaching speeds over Mach 3. Aircraft traveling at supersonic speed create a shockwave with a thunder-like noise known as a sonic boom, which can cause distress to people and animals below, or even damage buildings. For this reason, scientists around the world have been looking at sonic booms, trying to predict their path in the atmosphere, where they will land, and how loud they will be. To better understand how scientists study sonic booms, let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms a hyperbola, leaving a trail known as the boom carpet as it travels forward. This makes it possible to determine the area affected by a sonic boom. What about figuring out how strong a sonic boom will be? This involves solving the famous Navier-Stokes equations to find the variation of pressure in the air due to the supersonic aircraft flying through it. This results in the pressure signature known as the N wave. What does this shape mean? Well, the sonic boom occurs when there is a sudden change in pressure, and the N wave involves two booms, one for the initial pressure rise at the aircraft's nose, and another for when the tail passes and the pressure suddenly returns to normal. This causes a double boom, but it is usually heard as a single boom by human ears. In practice, computer models using these principles can often predict the location and intensity of sonic booms for given atmospheric conditions and flight trajectories, and there is ongoing research to mitigate their effects. In the meantime, supersonic flight over land remains prohibited. So, are sonic booms a recent creation? Not exactly. While we try to find ways to silence them, a few other animals have been using sonic booms to their advantage. The gigantic Diplodocus may have been capable of cracking its tail faster than sound, at over 1,200 kilometers per hour, possibly to deter predators. Some types of shrimp can also create a similar shockwave underwater, stunning or even killing prey at a distance with just a snap of their oversized claw. So while we humans have made great progress in our relentless pursuit of speed, it turns out that nature was there first.
Well, of course, nature's there first. They're always there first, right? Animals know what they're doing. That's why they've survived so long. All right. So, red shift and blue shift. Hopefully, you enjoyed that about sonic booms. I feel you guys never taught that. So, hopefully, you enjoyed that. All right. So, basically, red shift and blue shift is telling us how can we tell if planets are moving away or towards us? This is one of the biggest proofs of the Big Bang. Okay. Well, we need to understand something. Okay. If something is red shifted, we say that it's moving away from us. Okay. We say it's moving away from us. If something is blue shifted, we say that it is moving towards us. Now, some of you are thinking, well, why? Well, it's actually kind of crazy easy to do this. So when we look up at a telescope and we say, oh, that's producing a blue light, we know it's moving towards us. If it's producing a red light towards or that we see a red light, we say it's moving away. And the reason is this: when you look at the color spectrum, red light has a longer wavelength. Okay, it has a pretty long wavelength in the visible light spectrum. Blue light, on the other hand, has a pretty small wavelength, but a really high frequency. So, what does all that mean? Well, what it means is when we look at this, okay, we can say that that sun, sorry about that, let me get that out of your way. All right, the sun must be moving away from us because you have to think of that wave like a slinky wave. If I was holding a slinky to my eye and holding a slinky to the sun, as the sun moved away, that slinky would stretch out. And when it stretches out, the wavelength will get longer. And since the wavelength will get longer up here, that means it's stretching and it's going to be like a red wave. If the slinky was connected here to you and the sun, as the sun moved towards us, the wavelength would get smaller, the frequency would go up. And that frequency relates itself to blue light. High frequency light has blue, and low frequency light is red. That's where Roy G. Biv comes from. And we'll get to that in the next section as well. Here, this guy does a really good, his voice is a little different from mine, but he does a really good job in this video. So let's watch this video to try to clear that up.
The Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video.
So he does a great job with those visuals. That's very awesome to see. The deal is, like he said, almost everything we see in the known universe is moving away from us. So that is one of the biggest things to prove that there's Big Bang, that there's the expansion of the universe or space itself. All right. So until next time, guys and gals, I'll see you.